In today's video, we'll take a look at parametrized curves. So far, in this class, we've taken a look at functions of 2, 3, or maybe even more variables, and they take those in and they spit out a number in R. So these are functions from many variables into a single variable. Today, we're going to take a look at functions in the sense that go the other way. They take in one variable and they map out into 2 or 3 variables. So why do we care about functions of one variable that map into 2 or 3 dimensions? Well, the archetypal example is these model the path of a moving particle. So, for example, I could say the movement of a particle could be given to you by a function gamma from R for now, or a subset of R, into R3. And at every single time t, gamma is given to you by coordinates x, y, and z, all depending on t. All right, so if you imagine the movement of a particle tracing out a path in space, maybe this way, then at any single time t, it has coordinates x of t, y of t, z of t. Now there's also an alternative notation for this that's also pretty common. This is in vector form. You could model the displacement vector r of t, and that just gives you the vector with components x of t, y of t, z of t. So notice this is vector notation in terms of the ijk basis. And both of these formulations are equivalent. All right, so the vector notation is just telling you the displacement vector with respect to the origin 0, 0, 0. Your point traces out this path, and it's equivalent to just saying that there is also a function that's not really a vector with coordinates x of t, y of t, z of t. Let's now take a look at some examples of parametrized curves. And the first one is actually very familiar to most of you. And in R2, suppose you have any graph y is equal to f of x. Then there's an easy way to turn this into a parametrized curve. And this could be given to you by just setting x of t is equal to t. And if x is always equal to t, then because y is f of x, we just set y as a function of t now is just f of t. Right, so here's your picture. Suppose you had a graph y is equal to f of x. Then you can alternatively parameterize this by saying that every point lying on this curve has coordinates x of t, y of t, and this point just traverses along the path here. When you feed in at a given time t, it spits out both x and y. An important thing about parametrization is you should always give the interval parametrization. So if you want to capture an entire graph in this case, suppose you want a particle to be parametrized for the entire curve, then you might want to say time is between, well, it's for all time, so between minus infinity and positive infinity. You could also have a different parametrized curve that just gives you the path of this particle within a trapped interval. Let's say from time equals a to time equals b. Well, that's x equals a to x equals b. Then you might want to change time to from a to b just to capture the portion of the path between those two times. So those are oftentimes you also want to restrict the interval, so that's how you do that. Next, let's look at how we might parameterize lines. So fix a point with coordinates p is given by x naught, y naught, z naught. And let's say you also have a vector, which has components a, b, c. Now it's actually pretty simple to calculate and give a parametrization of the line that goes through this point P and travels in the direction of the vector v. So here's a point P, and here is a vector v. We can just write x of t, y of t, and z of t to be equal to, well, you start at the point x naught, y naught, z naught, and you translate by at, bt, ct. Now we see that at time equals 0, these all disappear and you start at the point x naught, y naught, z naught, and t, whether it goes positive, then you go in the direction of v, or if it's negative, then you go in the direction of minus v. This traces out a line that goes right through the point P in the direction of the vector. And so every single point here is on your path. And you want to capture this entire line once again. Your interval of parametrization is going to go from minus infinity to plus infinity. If you just want a portion of this line, then clearly you could restrict time as well, just to be in a finite portion. Finally, a very common parametrization we have is for circles. So remember that if we have a circle centered at x naught, y naught on the plane of radius r, then its equation, the unparametrized version of this, would be x minus x naught all squared plus y minus y naught all squared is equal to r squared. And let me draw a picture. If I have a center at x naught, y naught, I could pretend this is the origin, and this is my radius r all around. Well, if I think of polar coordinates, then it makes sense for me to set x minus x naught to be equal to r cos t, y minus y naught be equal to r sine t. Right, so here I'm pretending x naught, y naught is the origin now. So I subtract x minus x naught, y minus y naught to translate this to the origin. And by polar coordinates, this should be my expression for the points on this circle. And here I could say t is in between 0 and 2 pi. Now if we note how this travels, it says at time t equals 0, I'm at x naught plus r, because cos of 0 is 1, and y naught plus 0. So I'm here. As t increases to say pi over 2, I travel along this direction and end up here, and so on. So this gives me a counterclockwise parametrization of the circle. Conversely, I could also have a clockwise parametrization of the circle, right? Because oftentimes, well, given any scenario, even if the path of an object is circular, it could have either traveled counterclockwise or clockwise. Now, if I want to model something that's traveling clockwise, something simple to do would just be to set this as x naught plus r cos t, y is equal to y naught plus minus r sine t. We could check at t equals 0. This becomes x naught still, y is going to become y naught. At t, let's say, is equal to pi over 2. This is at x naught. And this is at y naught minus r times 1. So we're now at y naught minus r. It's down here. And then you could plug in at t is equal to pi. We're going to end up at x naught minus r and y naught minus 0. So we're here now. And we see by testing those points that our direction of travel is clockwise. So one thing we see from this above example is that given an unparameterized curve, you could parameterize it in infinitely many different ways. So here we had a circle, and we could parameterize it, well, first of all, as a counterclockwise path or a clockwise path. And clearly, as parameterized curves, they represent different movements. Furthermore, if we just adjust t to, say, 2t or 100t, then we could also traverse each of these paths at different speeds. So they all represent different movements even though they trace out the same path. You could think of the unparameterized version as just a path the particle traces out when you play the full video as time goes on. But if you want the precise location of the particle at each point, then you need to parameterize it, and clearly different particles could travel the same path at differently. You could see it in these examples as well. Here I could just once again scale the time variable so that I'm traversing the same path at different speeds. I could also change t to minus t and traverse this path backwards. Given a line, not only can I alter the speed at which I'm traveling this line by altering what t is, but I could also begin at time equals 0 at a different point along the line. If I just subtract, let's say, a, b, and c from x naught, y naught, z naught, then I'll begin somewhere down here, and then I could run the same, I could add the same terms here and travel along the same path, but at t equals 0, I'm starting at a point different than p, even though eventually this line also does contain p. Let's now take an example where parametrizations do matter. Suppose particle A travels on a path given by t minus 1, 4 minus t, and 2t minus 1. And particle B travels on another path given by 2t minus 7, 2t minus 6, and t minus 1. Now the first question is, do A and B collide? So what does it mean for these two particles to collide? Well, they must be at the same point in x, y, z, and they must achieve that point. They must be at that point at the same time t. So what we need is a solution t to the system where the x coordinates are equal, so t minus 1 must be equal to 2t minus 7. The y coordinates are equal, and also the z components must be equal. Now let's say if we just take this first equation, solving this first equation tells us that t must be equal to 6. But at t is equal to 6, the second equation for y tells you 4 minus 6 is equal to minus 2, whereas 2 times 6 minus 6, that's going to be equal to 6. And clearly these are not equal, so t equals 6, which solves x, does not solve the equation for y. And so we can conclude that these never collide. Remember, for particles to collide, they must be at the same point at the same time. And clearly, to be at the same point, all your coordinates must be equal. So for x coordinate to be equal, you must have time equals 6, according to this first equation, but at t equals 6, it does not solve the second equation for y. Now let's see if we can answer a different question. Do A and B cross? Now this is a different question than colliding, right? Because now we're asking if particle A travels one direction and particle B travels another direction, if you trace out their paths as t goes through the entire range of parametrization, do the images of their paths ever cross? This means that it doesn't have to be the case where they arrive at x, y, and z at the same time. We just want at a certain time for A, it achieves some point x, y, z, such that it's the same x, y, z that is achieved by B, perhaps at some other time. So what we need to solve is the following system. T1 minus 1 must be equal to T2 minus 7. And we have the similar equations for the other components. Now if we just look at the first two equations here, we could transform the first equation into T1 is equal to T2, 2 times T2 minus 6. And substituting this into the second equation, we have 4 minus 2T2 minus 6 must be equal to 2T2 minus 6. And we'll leave the third equation where it is. And so these together get you T1 is equal to 2 and T2 is equal to 4. So these satisfy the first two equations. And now we still have to check if the final equation is satisfied. So plugging in to 2T1 minus 1 for T1 equals 2, we got this is equal to 3. For T2 minus 1, well, T2 for equals, if T2 were equal to 4, then 4 minus 1 is also equal to 3, so this is great. This means that T1 and T2 are consistent, and yes, there is in fact a values T1 and T2 such that these systems are satisfied, which means A and B do cross their paths. That means they arrive at the same point, x, y, z, but possibly at different times. Here, A arrives at time equals 2, and B arrives at the point at time equals 4. Here are some exercises for you to now try by yourself.